Copper price time series forecasting by means of generalized regression neural networks with optimized predictor variables. The present paper was written by researchers of University of Oviedo and the Central Mining Institute of Poland. The target of the present paper is to forecast copper prices in the next 12 months. To this forecast, we are going to optimize the predictor variables used in a generalized regression neural networks. To achieve the target of the paper, we followed two steps. The first one was to obtain the site of the latest variable. I mean, we have a lot of prices of copper, and the first we have to do is to find how many of these prices we need to form the lagged variable that we are going to use to feed the neural network. To obtain the site or the optimum site, first we obtain an approximated site of the variable, and then we mark a range down and up for this approximate value to get the better site of the lagged variable. In this process, we need to add figures of merits to know if we are doing good or bad. And to measure our errors, we use the root mean square error and the mean absolute error. And later, we complemented with the standard deviation of absolute error. But our principal errors are the root mean square error and the mean absolute error. Okay. In the second step of the paper, we introduce more information in the lagged variable, consisting to put the order of the prices inside of the lagged variable. And we found that the result was better because the error decreased. They don't decrease very much, but they decrease. So we get a better forecast for the copper prices. The data we used for our paper was the monthly copper prices in the London Metal Exchange market. This is one of the most important metal markets in the world. The prices were collected by the World Bank in a World Bank pink sheet done in Excel. So we collected the data from the World Bank. As the neural network we are going to use is a trial and error method, we divided the data in two groups. One group was the training group or the training data set, and the second group was the validation data set. From the training data set, we started to work with the neural network with 704 values, and for the validation we used 12 values. 12 values because we wanted to forecast the price for 12 months. This is the reason of the amount of each group. The first thing we did with the source was a plot representation to know about the form of the data, and in order to know if we can use the data with the different neural networks. Achieving the mean and the variance stationary using a logarithmic transformation and a second-order differentiation with a period of 28 months, we discovered that no seasonal component were available. Among the alternative approaches to get the size of the lagged variable, according to Turner and Fine, we estimate a first value for the lag variable. The equations we use from Turner and Fine are on the sheet, and the key value represents the size of the lag value. Taking into account that the key is the size of the lagged value, with the 704 prices of Copper, we obtained a key value of 24 sites. Taking into account that this number is an approximation, we decided to make a weighted study not only for k equal at 24, but with k from values from 12 to 36. In this sheet, we have the case of k equal to 5. It means that we have a lag variable of 5 times the light input temps. In the table, we can see the first 10 lag variables we are going to train the neural network. In our study, we use lag variables using sites from 12 to 36. In case of a lag variable of 12 values, I mean it includes 12 Copper price, 12 Copper prices, we used 683 lag variables to feed the neural network. From 12 to 36, the number of lag variables were decreasing. So in the case of 36, I mean the lag variable with 36 numbers, 36 prices, we use 669 lag variables, and it means that if the number of the prices contains in the lag variable is bigger, I mean the lag variables we can use is less. So this is the reason we use different lag variables depending of the input temps of the lag variable. Well, we feed with this data, we feed a software program from Paralyside of United States, and we obtain the next results. As we can see in the table, the best result it was obtained with a time delayed input temps of 36 values. For 36 values, the root mean square error and the mean absolute error are the less possible in the table. In the second step of the paper, we did the same work like in the first step of the paper, but introducing new information in the lag variables, consisting in to mark the order of the input terms of each lagged variables. For example, in the sheet we can see, in the case of 12 terms for the lag variables, not only the 12 terms that formed the lag variable in this case, and also the order of the importance of each lag variables. As we can see in the table, the result in this case was different, and we obtained the best result for a lag variables with 27 input terms. In this case, for 27 input terms, the errors are the less possible. So, introducing the order of the input terms, we improve our results. Once we trained our neural network, it's time for forecast. In this case, the validations data that we are going to use is the last 12 months of copper prices. That means from September 2018 to August 2019. In this case, in the table, we can see the forecast for the last 12 months, taking account we are using a year neural network with 27 input terms in our lagged variable, and the errors are in the table on the right. If we compare the forecast and the real prices, we can see in the plot draw that in the first 6 months the forecast is very good because it's very close to the real prices, but in the last 6 months the real prices are higher than the predicted prices, and there are significant difference between both plots. So, in conclusion, we can say that our prediction will be good for the next 6 months, but not for the second 6 months. I mean, we can have a good prediction for the first 6 months we want to forecast, but not for the 12 months. I think this method is good and results are good for the first 6 months. The conclusions of our paper are: the first one, in cases as the one analyzed in this work, there is no proper method to select the optimum site. The second conclusion is including the order is good to improve the forecast. And in the third conclusion, this method of the year neural network is able to achieve for the first 6 months forecasting. After the 6 months, it's not a good idea to use this method. Thanks for your attention.